Good morning. So, not so many people. I think that, okay, this gives me the possibility to go slightly around the things that we have seen last day. So, we talked about, let me come to the right place. This morning it will be a little more technical, but still, yeah, I can stop here. We saw that for linear problems, I used this notation for, this is changed. This is the notation for inverse problem, and this is the notation for parameter estimation. But in both cases, the problem and all the equations are written in the same way. So we talked that even for the very sample case, where we have a Gaussian likelihood and a Gaussian prior, the posterior probability we know, it is Gaussian. So it means that if we can compute the mean and the covariance, then we can do any computation. However, we saw that when, in particular for inverse problems, when the size of the f is large, or even for parameter estimation also when the size of theta is large, then this matrix is very large size. And so using these two equations to compute the theta hat and v hat is not practical. For theta hat, if we were only interested by computing theta hat, which corresponds to the posterior mean and posterior mode and posterior median even, then we can do it through the optimization, because it is easy to show that this is the solution of this optimization of this criterion. And this criterion is quadratic, and its optimization can be done very easily. But the computation of V is more difficult. Yes, for the computation of theta hat, as I mentioned, we have to optimize this criterion. And the optimization can be done, for example, one of the techniques, the easiest technique, is gradient-based, because we can compute here the expression of the gradient. And then, if you look at the algorithm, iterative algorithm, we see that finally, to implement this algorithm, we do not even need to have the matrix H inside the memory of the computer. The only thing that we need is to be able to compute H multiplied by theta and H transpose multiplied by this difference. Okay? If I call D hat to be H theta hat at the previous iteration. So this one is called forward equation, forward operation, and backward or adjoint operator. So if we write only two subprograms, where if we are given theta can compute D by any way, actually very often we do not need to have H completely. The matrix H very often is defined by a very lower number of the parameters. And then, if we can do this, we can also compute this one. But the second part, which is if we need to compute the covariance matrix, then the situation becomes much more difficult. And what are the different tools? Yesterday I mentioned. One of the tools is that in particular cases where the matrix H has some structure, for example, in convolution, the matrix H is Toeplitz. If we can transform the problem in such a way that the matrix which is Toeplitz becomes circulant, then we can use FFT techniques to compute its inverse. Second approach is iterative way and Kalman filtering. I am not going to talk much more about this in this talk. And then I am going to talk these two approaches a little more. For the first one, as I mentioned, if H is circulant, for example, or block circulant, then it can be diagonalized with a Fourier transform and inverse Fourier transform operations. And lambda here will be a diagonal matrix whose diagonal is related to the Fourier transform of the first column or first line of this circulant matrix. A circulant matrix is a matrix where the first line, if you have the first line, you can obtain all the other lines by circulating in this way. And if H is in this form, then it is easy to show that the whole matrix that we need to inverse can be obtained also in an easy way. The second approach, which is more numerical techniques, very often the whole covariance matrix is not usable or is not desired. Very often, if we can only compute at least the diagonal elements of the inverse, it is enough for many applications. Or probably if we can go a little more, having the first off-diagonal terms too. The problem is that we have a great matrix, and we want, for example, to find an approximate inverse of them. Again, here also the technique is try to put the problem as an optimization. If I call A to be the approximate inverse of B, and we can define a kind of distance between them, and then use this distance to transform the problem to an optimization. Between the different distances, one is very interesting, this one, because it is related. So we are talking here as the matrices, A and B to be the matrices. We are talking, and if these matrices are associated to the covariance matrix of the probability distribution, it can be shown that then if sigma 1 and sigma 2, I could put it A and B, but doesn't matter. Consider the problem that we have this posterior probability, and we want to approximate it by something which has a simpler, for example, a diagonal covariance matrix. So if we look at the expression of the Kullback-Leibler distance between Q and P, we can put it in this way or in this way, then we can again transform the problem of probability approximation or the problem of approximating this matrix by something which is diagonal, the same problem. So this expression is I used actually this expression to do this, and this interpretation is nice because what does it mean having a covariance matrix which is diagonal? Means that you are assuming that it is the components of X are separable, and this separable approximation of a non-separable probability distribution is the main objective of many variational Bayesian approximation. Okay, so and the third category are sampling method. Imagine that you have this posterior probability which is Gaussian, and you decide to generate sample from it. How we can generate samples from a Gaussian distribution? Actually, if you can do a Cholesky decomposition of this matrix, and if you can generate a separable Gaussian components, then it is easy to show that if you do this transformation, U is here, A is here, and F hat is obtained by optimization, then this F will be one sample of this posterior probability, and you can generate many samples and then use it as do any statistics or any inference on that. But the main difficulty, of course, is here how to do this Cholesky factorization. A second technique which does not need this Cholesky factorization is very interesting because it is related. It is obtained. This technique is called perturbation optimization, and the main idea is, okay, consider X to be this, which is actually corresponds to the mean that we can compute by optimization. Okay. Now it is easy to show that expected value of X is F hat, and the covariance matrix is sigma hat. This can be done using the matrix inversion lemma and going through the computation. You can show it. So this is interesting. What does it mean? It means that if we can compute X many times, this can be done by optimization, as we mentioned before. Then we know that the properties of X is such that the expected value is F hat and the covariance is sigma hat. So what will be the algorithm? The algorithm is to generate two independent random vectors, Gaussian random vectors, add this one to G, it means to the data, this one to the prior, and do the optimization with these two transformed quantities. Okay, we know how to do this optimization and repeat this process many times, any times that you want. And at the end, you can keep these samples and compute anything that you want from that. This is called perturbation optimization. And one of my colleagues has worked on that, and they have published. You can get the references in the reference part of the book. Okay, so the idea is sample. So this is the main property which is used. So distinguishing that this one can be obtained by optimization. Okay, so how to generate the samples? This is the way. Remember, you add a Gaussian vector that you generate to the data, a Gaussian vector to the prior, the mean of the prior. You do optimization, you get one sample. Again, repeat this operation. And from those samples, then you can do anything that you want. Another technique which another group of other people of my group has worked on is a little different. Still all the time is by optimization. It starts by initializing these two vectors, finding these two matrices, diagonal matrices, and then optimize this. So it means the criterion now is no more just here identity are given these two diagonal elements. It means that the problem is, again, an optimization, but weighted optimization. And so, again, here, two random vectors, the same operations of adding, computing delta G and delta F, and computing, again, the vectors V, F, and VE, and repeating this operation. And again, it can be shown that these samples are, again, from the posterior probability. Okay, so these are the different sampling, but still, as you can see, they need, for generating each sample, you need to do an optimization which is done in an iterative way. Okay? But still can be applied. That was for the Gaussian case. Unfortunately, very often we need to use other terms for the likelihood when the noise is no more the Gaussian, or other priors which are no more Gaussian too. For example, for the sparsity enforcing, very often the people use something which is a probability distribution which is very concentrated around the zero and has heavy tail. And one of these is, for example, double exponential. Using this double exponential with this likelihood brings us to the optimization of this criterion, which is called in regularization methods, which is called L1 regularization. And the fact that now the criterion does not admit regular gradient, because the gradient of this term is not defined as zero, there has been a need to develop special purpose techniques of optimization for this case. A great number of the optimization techniques have been developed for this case, which has the name ISTA, FISTA, ADMM, and so on. And many great number, lasso, many great number of optimization techniques has been used to be able to compute this. But this again corresponds to the mode of corresponds to the map estimate. Again, very often the people who do regularization methods, they do not care to compute the posterior covariance, for example, and the covariance optimization still stays difficult. Okay, yeah. What we can do in these cases, if we are able to compute the posterior mode, this we saw that, okay, this is possible to do by doing this optimization. More sophisticated algorithms are needed, but still it is possible to compute the mode. And then what we can do is trying to do what is called Laplace approximation, which means that we try to approximate this posterior probability by a Gaussian centered on the mode that we have computed. Again, here, unfortunately, this matrix which is needed to be able to do this computation is a very huge size, but at least it is possible to do this. We can do, for example, not compute all the elements of A and only the diagonal elements, and it will be, again, a coarser approximation of this posterior. Okay, for why we need to do all these in the previous problems, I just mentioned computing the posterior. But in machine learning problems, there are many other things that you need to do. For example, you need to do model comparison for doing model selection. You need to do sometimes prediction. So if we look now at this expression of the posterior for different m, I didn't put m in the previous slides, But here, because very often the problems that arise in machine learning is to do model comparison. You can see that for doing model comparison, we need to compute these integrals again. And for the prediction, we need also to do these integrals. Let's see for those problems, what are the different approximations. Again, you can find Laplace approximation, Bayesian information criterion, variational Bayesian approximation, which is we have developed much more this part, and many other techniques. Let's go a little through some of them. Laplace approximation, just I have explained. The main idea is first to compute the mode, and then develop actually the minus log of p around this mode in Taylor series and keep only the second order. And in this case, if we are able to compute the elements of A, it can be shown that, for example, for the model selection, the expression that we need to compute will need to compute the determinant of A, but okay, in the reasonable size of theta, it can be computed, and we have a good approximation for the evidence to do a model comparison. BIC is goes still a little more in approximation, assuming that the number of the data is high enough for the big data. This approximation is valid. It can be shown that this likelihood will be dependent only on this number n, and then we can use it in great dimensional approximation. Very often in machine learning, we have not only one layer, we may have many layers, and so we have not only we have data which are related to the first level unknown, and then and also this theta. This first level unknown is called hidden variable, and again the problems that we have with this hidden variable part. Again, we need to do this kind of computation, and the integration becomes no double integration. In those cases, again, doing exact computation are very difficult, and we can use this Jensen's inequality, which gives us the possibility not to compute exactly the evidence, but to have a upper bound or lower bound, depending on what quantity you are interested in, for that. And these relations can be extended. Let me go a little through the details and to see how these things are going to work. And it can be shown, yeah, here, it is important to mention this. It can be shown that this term, which is, for the particular case, that this Q that we are going to use here is separable in hidden variable and parameters. This can be shown that this quantity, which is defined here, which is called free energy, is exactly the lower bound of the evidence. And if we go a little more through the details of the development, we can see that these two terms that we need to compute looks like a EM algorithm, which is very well known as an iterative way to compute the evidence. what? Yeah, these two. These are for the particular case of the inverse problems, or for the Bayesian approach in general. These two equations can be written in this form, and if we do a comparison here, I haven't time to go through the details of the EM algorithm, which is very well known. I wanted just to show what are the differences between the two. Here I put the equations which are standard Bayesian EM, expectation maximization, and this is the variational Bayesian one. And if you look at the two, you can see that in variational Bayesian EM actually is a particular case of a particular case of this variational Bayesian model, for which this second expression is only a deterministic one. Okay. I think that I have prepared a little more details about variational Bayesian approximation that which gives more details about these differences. Okay, let me give a little more, some references and a little more about the main part of the general variational inference. The main idea is, as I hope that this is not difficult for you. Sometimes I have used D and theta, and sometimes I have used G and F. But the same as I mentioned, that depending on the different applications, but all the equations are the same. Just the notations are slightly different. The main idea is, okay, we have data. Yes, we have data. We have the hidden variables f, and if we call both these x, just to write the things easily, the main idea is that if p of x can be written in this form, this is particularly these methods have been developed for the Bayesian networks, and in the Bayesian networks, each node is depend on the parents and the children, and very often in the Bayesian network, it is possible to write the expression of the probability as to be a product of conditionals to the parents xi. And for example, here exactly to make the context applicable for the case of inverse problems, f is exactly the unknown, g is the data, and x is the combination of the two. And the goal of the variational Bayesian, as we will see, will be try to approximate this by something which is more easy to handle. The main ideas is that, okay, we want to approximate a probability distribution P by a probability distribution Q. The criterion to use is the Kullback-Leibler, and just using this Kullback-Leibler, it is easy to show that the evidence can be written in this form, sum of these two terms. So minimizing the Kullback-Leibler or maximizing the free energy will become equivalent. And in both cases, we find an upper bound for the evidence that is needed to be computed. Particular case of separable factorized form is called mean-field approximation, which is very well known. And if we apply now either the find the expression of the free energy or find the expression of the Kullback-Leibler and doing going through this optimization, we can find that finally, let me go a little faster on that, we can find that, yeah, this is the point. We can find that this optimized factorial form can be written in this combination. And so, as you can see here, to be able to compute this, we need only local computation. And this local computation involves the sum of the terms, which involves the parents and one term for each of the child node. The details of the development to arrive at this is very standard. You can find it in many reference papers. And it is a great number of the methods which are called message passings are based on this. Actually, these terms, we will see a little later, these terms in general are called messages from the child from one node to the child nodes, or from the parent, one node to the parents. And in particular, computation of these terms, these expectations which are needed here, will be facilitated if for the exponential family. And if we apply these equations for the case of exponential family, let me go fast on these details. What we obtain at the end is this. And looking at this, we can distinguish the terms which we can call it messages from each node to the child, and messages from a child to the parent, and we will have these two expressions. And as you can see, these two expressions can be computed very easily for the particular case of exponential families. This is a little details that in the node, which is formed by the data and the hidden variables, for the observed data, the messages, the expected value is just given by the observed value, and then we can write it. Okay. Actually, all the variational inference, you have two categories. One is based on minimizing the Kullback-Leibler of P over Q. The other one is based on Kullback-Leibler of Q over P. And the expectation propagation techniques exactly are in the opposite of the variational Bayesian approximation. Tries to optimize this to do the same variational approximation, but this time minimizing not Q with respect to P, but P with respect to Q. Again, let me go through some of the details. The main assumption is that we can write like this. This is the case of the Gaussian, this is the case of the Bayesian, this is the prior, and this is the likelihood. Very often we can write the likelihood of the whole data as to be the product of the likelihood corresponding to each subset of the data or each data. And going through these computations and trying to write the expression of the KL and minimizing it, you will find a few other notations or expressions. For example, KVT distribution, tilde distribution, and then let me show the algorithm, how it is work. You start by an initialization. Then you compute this cavity distribution. The expression of this cavity and tilde distributions can be obtained by just writing the expression of the KL and computing the derivative with respect to them. And as you can see, these are the different steps. But let me, there are again many different kind of methods which has been developed. But let me insist on this, only on these differences between the two parts, between the two category of techniques. These are the main point actually. Assume that P is exact. I am going to summarize. Q is the approximate one. In VBA, we try to find this approximate by minimizing this. If you look at the expression of KL, because Q, the integration is with respect, the integration Q is factorized, so it is much easier to write the derivative of KL with respect to each factor, put it equal to 0, and obtain the VBA algorithm. However, doing this means that the obtained factorized form recovers well the high region of P, which means that we are going to estimate well the mean, yes, the mean and the mode, but not very well the higher order moments, and in particular the variances. So we know that in this approach, we do this approximation. Mode and mean are very well approximated, but not the variances. At the other side, all these expectation propagation methods try to do at the other side this optimization. The computation is much more difficult because Q, which is all the integrals are multidimensional integrals, but yes? VBA, yeah, oh sorry, yeah, you're right, you're right. Yeah, this is VBA and this one is EP, yes, the title. Thanks. I tried to do these slides last night, actually. Added these slides to try to understand these things. Okay, yeah, this is EP. EP, expectation propagation, tries to optimize, as I told, at the other side. And so this means that the recovered Q, the obtained Q recovers all the more on the tails of the distribution. So it means that we are going to well approximate all the higher order moments. And it is more difficult to compute this than this. In particular, depending on the domain of application. In Bayesian networks, each node is related to a few number of the child or parents. So both methods can be applied, and due to the fact that this expectation propagation, gives more accurate estimate of the higher moments. In Bayesian network, EP has been used more often. But in inverse problems, remember that each data is related to the F in a very dense way, very often. In some cases, for example, in convolution, if the size of the point discrete function is not very large, okay, this dependence is local. But in computed tomography or in Fourier inversion or Laplace inversion, unfortunately, this is not the case. And so applying this expectation propagation is much more difficult and much more costly. So that is why we developed, for the inverse problems, more variational Bayesian approximation. Okay. So I hope that I could transmit the main ideas between the two categories of the methods. Both are focused on Kullback-Leibler. One is trying to minimize KL of P with respect to Q. Another one is Q with respect to P. What are the differences of the properties of the solution that we obtain? And as I mentioned, for the general inverse problems, variational Bayesian is much easier, and we have used it. Let me go a little more through inverse problems, which is the domain on which I am working, and show you some of the applications. Computed tomography, I hope that everybody knows about the computed tomography when we want to see inside of the brain. Okay, seeing outside of something is easy. You send light comes back, you take a picture, and you can see the outside. But to see inside, you do the same, send a wave, but this time the wave has to go through the body, and either by reflection or by transmission, you measure something, and from this data, you try to give a picture, an image of the internal property of the body. Here is the X-rays. X-rays are going through the material. At the other side, you measure the attenuation. And from the physics of the problem, X-rays goes through the straight line. And it is easy to write the relation between the data that we obtain and what is unknown. What is unknown? This unknown represents the variation of the density of the material in a section of the body. Okay? And we know, for example, that tumor is more dense than the soft tissue around. So we can, looking at this image, this reconstructed image on the computer, we can infer on, we can see the inside of the body. This is an example not in medical imaging, but in non-destructive testing application, where you have a metallic object, and you know that there may be a hole inside, and you are looking to see the shape of this hole, if there is, to decide if it is dangerous or not, and you obtain different radiographies around, and from these radiographies, you try to find a 3D representation of the inside of the object. Okay? For the 2D case, actually, if you do all these things for one line or one section, you obtain this kind of pictures. Let me go a little more through the 2D case and see how the things are discretized. This is the object space is discretized in pixels. So we can say that this image is pixels f1, f2, fn, and one of the lines of X-rays, which gives us the data GI, is related to the values of f through this line, and this section, which is the length of the ray I in the pixel J, is exactly the elements of the matrix H that we need. Okay? So as you can see, this matrix is very high dimensional, but the number of the elements in each row is very, very few. Okay? And for 2D problem, you can see that f is the size of this. For 3D, it becomes this. So the size of this matrix is this multiplied by the number of the data. so very huge dimensional. Hopefully, in this case, the operation of forward and backward projection can be done very fast, for example, implemented by GPU and doing this computation very fast. So we can apply these optimization techniques that I mentioned for this application, even if the size of the vectors f and g is very high. Another way to see the inside of the body is not using X-rays, but using microwave or ultrasound. This time, the waves goes through the body, and the equations are much more difficult, wave equations that you have to write, and the problem is nonlinear, and it can be written in the form of two equations. G are called green functions. The observed data are related to the object, which is the variation of this function that is needed to be reconstructed. And as you can see, this second equation, this equation makes intervening use of an intermediate quantity, which is the field inside of the body. So these are the equations, nonlinear equations, which relate the data to f through phi, and phi is at the both sides of this equation, which is an implicit equation. So the whole system is nonlinear. If the object was very low diffracting, then we could do this approximation and the problem should become linear. But this approximation is not valid all the time, and in particular if the contrast function is high, but still no problem. We can handle these equations in the discretized form, and I will show you how to use it. Yeah, these two equations can be written directly as the original one, or sometimes in place of using f, we introduce another term, which is the product of these two terms. And why this is used is that these two equations becomes no with respect to w and f. It will be linear equation here and linear equation here. So we have transformed the nonlinear equations to a coupled bilinear equation. Okay? Two linear equations which are coupled to each other. Okay. To be able to go through all these different steps, I am going to summarize everything through this kind of graph, which gives us the possibility to see what we are doing. We introduced a lot of details. Let's go slowly, starting by the very sample case, and we go through the different steps. The very sample case is when the data are related to the unknown. Okay, we can write the likelihood, we can write the prior, we can apply the posterior probability, and the only thing which is unknown is f, which is in red. You can remark that I put in blue the data, in red what is unknown, and there are also these hyperparameters. For example, variance of the noise, or variance of the f, or all the parameters of the prior model, which are unknown. If these parameters are known, I put it in rectangle. So this is the graph of this very sample problem. The hyperparameters are known. The only unknown is f. We have the data, we apply Bayes rule, and everything is okay. In practice, in practical applications, variance of the noise, theta 1, we do not know. And also the prior model that we give for the problem may depend on some of the parameters which are also unknown. We say that this is the supervised method, for example. If it is unsupervised, it means that the theta 1 and theta 2 are not known. So no, they became red. It is possible, again, using the Bayes rule, compute this joint posterior of f and theta by adding some prior probability on these unknowns too. We can use conjugate priors, for example. And so the graph becomes this. In this unsupervised method, not only we obtain f, but also we can infer on the hyperparameters of the likelihood and the prior. Okay? I will come back on this a little later, more in detail. You remember that in some applications I talked about sparsity. Again, the same model, and now f is, we know that it is a sparse. What does it mean, sparse? It means that very often the values are near to 0, and sometimes it takes a high, very high value. How to translate this in a prior probability? The idea is easy. We need to assign a probability distribution to f, which is concentrated around 0. So the probability that the values be near to 0 is high, and have high tails. Okay? What are the different possibilities? In a paper, I gave many probability distributions which have this property. Mainly, we can divide them in 3 categories. A generalized Gaussian, which particular case is double exponential. A double exponential is like this. But any other generalized Gaussian one can be used. The second one category is the mixture model. Imagine a Gaussian with a very narrow variance and another Gaussian which has high variance, and you do sum of the two. You obtain something which is very narrow, near to 0, and very large in the tail. These 2 categories, we have used also them, but doing the computation with them is not so easy, Bayesian computation. This one is not so easy because due to the fact that for the double exponential case, it was, the gradient was not defined at 0, so we needed to find optimization algorithms which are very particular. And this one also is not so easy because, for example, Bernoulli Gaussian model, it combines the, say, the discrete and continuous variables, and doing the computation with this are not so easy neither. We opted for a student T that I explained in the first day. And what is the main interest of the student T? If you remember at this integral of Gaussian and gamma mixture distribution, this expression gives us the possibility to say that, okay, to be able to model f by a student T, we can go through a hierarchical model introducing this variable z, which is the inverse of the variance, and this z is a gamma distributed. The combination of these two means that f is modeled by a student T. And what is the properties of a student T? Compared to the Gaussian, for example, it has higher tail and more concentrated around the 0. Okay? So by doing this, we are not going to use directly this, but we are going to use it through this hierarchical model. So what will be the scheme? This time G depends on F, okay? But F, no, we could directly put this, but doing the computation directly with the student T would not be easy. What we do is F depends on Z, and Z is gamma. So we have now a hierarchical model where we are going to estimate F and Z, and also why not, the variance of the noise. Again, we can write the joint probability distribution of everything, and then we can do computation with this joint posterior. Why we can do no computations much easily? Because gamma distribution is a conjugate for the normal distribution, so we have a conjugacy here. Here also we have a conjugacy. So all of these probability distributions are in the exponential family. So developing and implementing any variational Bayesian method would be much easier. And each time during the iterations, you handle only Gaussian and gamma distribution, which are very easy to handle it. Okay? So to model the sparsity, we went through, in place of directly using this probability distribution, we went through introducing a hidden variable and trying to estimate it indirectly. For that bilinear equation, these are the two equations. Again, so the problem was nonlinear. With some trick, we transform it in two equations which are linear but dependent through we can say a hidden variable. So again, we can make the scheme very easily. G depends on W in a linear way. Here is. And W depends on F, again, in a linear way. And all the parameters, the variances, and so on, may be known, may be unknown. We can also handle the hyperparameters too. Okay? So, actually, giving this scheme, we can see that, okay, all the computations, again, we can do it very easily, because each time the relations are linear everywhere. And very often we can do with the Gaussian approximation of the errors, do the computations very easily. Yeah, this is the case where the hyperparameters are not known, but doesn't matter, just the extension of the previous case. Okay. Coming back again, for the sample case, I mentioned that we can obtain the expression of the posterior. And then what we can do, very often we can be satisfied by just computing the map solution. Okay? This makes the relation, the link with all the regularization methods which are very well known in engineering, in computer science and engineering departments. And they are used to many, many applications. But the advantage to be Bayesian is that not only we can be contented, we can be satisfied with this solution, which is one part of the Bayesian approach, but also, as you could see, we can apply all these approximate methods when it is possible to compute posterior mean and the covariances exactly we can do, And when it is not possible to do exact computation, we can do this variational Bayesian approximation and give the covariances as a extra information with respect to the regularization method. Okay, for this scheme, for the case of the Gaussian, everything is Gaussian. We have wrote it, all the details before. A little detail is that sometimes the prior probability that we use, it can be a prior which is separable in the components of F, and sometimes we and sometimes we may use a Gaussian distribution for which we know a priori that the covariance matrix is not identity. Okay? So if the covariance is no more identity, very often we can put this covariance matrix in this shape, and what is the interest to put it in this shape is that when we are going to do map estimate, we have a criterion to optimize, which is no more this, but this. The only difference is the presence of this D, which shows the a priori dependence of the elements of F if we know them. Okay? And then all the equations can be written also very easily. For the unsupervised case, again, all the things we can do it, but the fact that this time we have two quantities to infer, either we can do joint map, but also, exactly, this is in this place that I am going to give a little more details about the VBA and to see the differences with respect to all the other techniques. As I mentioned yesterday, if we can write the conditional of F given theta and theta given F, we can use Markov sampling, keep sampling. But each step here, the step here is high dimensional, and I mentioned that for this high dimensional sampling, we need special purpose techniques. This one is, in general, low dimensional, and everything can be done very easily, but this step is costly, and we can do this step, again, by perturbation optimization technique, for example. And finally, the variational Bayesian approximation, which the main idea is that the dependency of F and theta is very weak. So by doing an approximation, separable approximation, we do not do a huge approximation. So this is the technique that I will give a little more details. So let's see, we have the joint posterior. We can just optimize with respect to F and theta, obtain the solution. Okay. We can marginalize with respect to F. Sometimes it is possible to do. Then estimate estimate theta. And when theta is given, we come back to the previous cases and we can compute F. And the main idea of the variational Bayesian is, okay, first approximate this by a separable distribution, and then infer on F or infer on theta separately. Let me show the difference between these three steps. If I develop a little more this variational Bayesian and go through the equations and so on, we will see, let me go fast on that, yeah. We will see that actually this variational Bayesian approximation, let me a little come back here, yes. We will see through these equations that it is an iterative algorithm. We need to compute Q1, but to compute Q1, we need to do this approximation with respect to Q2. And then to compute Q2, we need to do this approximation with respect to Q1. And we can do these operations if we choose particular structure for Q1 and Q2. Exactly, exponential family and conjugate priors gives us the possibility to do these computation of expectation and these updates very easily. And let's see what are the different choices. If I choose these degenerate or deterministic distributions, okay? Just I say that, okay, Q1 is this, Q2 is this. So now I have to iterate f tilde and theta tilde. If I put it in the equations, I will see that actually this becomes alternate optimization of the joint map. Okay? If I choose for theta to be a Dirac, deterministic, but for Q1 I choose something which is proportional to the conditional distribution of f given theta, then I obtained the equations of expectation maximization. And for the general case, we do not do any of these particular deterministic models, and we leave all the probabilities to be updated during the iteration. Let me show it in a graph. This will give us some insight. How it works, this joint map, the first case. You give some initial value for theta. Okay, if the theta is known, you can do map to obtain f, then use f to obtain theta, and go on. What is the main inconvenient, main drawback of this approach? We initialize with theta and obtain a solution for this. And then we are going to use it as it was exact. But we know that it is not exact. We do not account for the uncertainty of f tilde, and we use it as it was exact to compute theta. And theta, we know that it is not the exact value, no, not yet, but we are going to use it as it was exact. In the EM algorithm, for theta at one step, we know that it is not exact yet, but we are going to use it as it was exact. But for f, no, we compute actually the whole probability distribution, and this probability distribution is used to update theta. And finally, for the variational Bayesian, we account for all the uncertainties at each iteration. Okay? We initialize this Q. In place of computing, we are computing Q1F, actually we accounted for the uncertainty of theta, and now we transmit the message to the next step, but this message is the whole probability distribution, which is used to update the probability distribution of theta. Yes. So as you can see, in this way we can obtain a better result. Okay. I think that I am a little late. As we applied this for the particular case of sparse method, all the equations can be written, and we can apply this variational Bayesian approximation in this case too. Let me go through this. Let me show another model which is very well used in many image processing applications. In many image processing, you have this image, which corresponds to the value of f. Very often, you can distinguish the region and the material inside of each region can be in a finite number of the materials. Okay, I will show you an application here. And how to model this? We can say that, okay, all the pixels which are inside a region, for example, this region, which is the color red, all these pixels are homogeneous. How to model this homogeneity? We model this homogeneity by a normal distribution with some mean and some variance. But this is conditional to knowing that we are in the region K. And now, if we can model also the property of this segmentation result, Z, we can put a Markovian model on Z. And because why we can put a Markovian model here is that, for example, when I have a one pixel here, this pixel depends on the surrounding area, and this is given by this Markovian model, and so the scheme becomes like this, and we can write again the expression of the joint posterior probability and apply this. Let me. You can see that we can more and more complexify the prior model, and also, for example, complexify the forward model to account, for example, for some background in the data which may be unknown. Anyway, for any of these different cases, we can make these graphs which relates everything to other. And almost everywhere, we can use Gaussian and gamma distribution in many cases, and they give valid results. Let me go fast also about this. And let me show one of the applications. It was in the convolution of mass spectrometry. We are looking for such a signal, which is sparse. We used this sparsity prior and apply it and look at the results that we can obtain compared to some of the standard techniques. Many standard techniques of the convolution could not separate, for example, very close peaks, but with our method we could separate these peaks, and not only we could separate them, but also we could put error bars, because we were able to compute the posterior variances and put the error bars on the solution. Much more applications. Let me just mention one, where we compared, because this Bayesian variational approximation is an approximation for the posterior probability. Many questions we get. Did you compare a MCMC solution with respect to the variational Bayesian? Yes, we compared. And here is, for example, in one of these applications, the comparison between the solution that we obtained by MCMC, which needs a really very great amount of the time, compared to VBA, and sometimes even if the variational Bayesian approximation is an theoretically approximate solution, the results were better interpreted from the physics of the problem. Yes. Okay. I wanted also to give some of these variational approximation methods in other applications of machine learning, in classification and clustering. In the same way, you have the mixture models. In these mixture models, you have the expression of the probability distributions that you want to do this clustering or this classification by doing approximation. Again, all these techniques of approximation can be used in the mixture models, but I think that it is preferable that I stop here and leave the place for some questions if there is. Thank you.